Thank you. Hello, everybody. I am very glad to give this talk to the bright students of the Nuclear Engineering Master Program at Pisa University. My talk is about virtual reactor, which is a computerized simulator of a nuclear reactor. In the past, a reactor simulator had to be made with a lot of approximations and simplifications because of the insufficient computing power. Therefore, the solution fidelity was not enough to replace verification experiment. Rather, some empirical formulas obtained from the experiment had to be provided to the simulation codes. But now with the enormous increase in the computing power, particularly with the GPUs and also with the continued development of the modeling method, it would be possible to make high fidelity simulators which can faithfully represent the reality. Then these high fidelity simulators or virtual reactors can be used to accelerate the development of advanced reactors by reducing the required experiments and by raising the confidence on the predicted reactor behavior. I'm going to talk about this possibility in this talk. First, I will start with the difficulty of high fidelity reactor simulation and talk about conventional reactor simulation which had to involve approximations and simplifications. I will then present the elements of the virtual reactors for advanced reactor development. After showing various advanced reactors under development, which are much more complicated than the conventional ones, so that a more sophisticated modeling is necessary. Then I will introduce the GPU-based high-performance simulation involving Monte Carlo and CFD calculations. Finally, I will touch the potential of machine learning and the digital twins to be used in virtual reactors. This is a nuclear reactor which consists of fuel assemblies and coolant. Each of these tiny regions in the fuel and coolant has different power and temperature. The total number of regions to be traced is more than 760 millions, which is a very large number. The power and temperature distributions are determined as the result of the interactions between several physical phenomena occurring in a nuclear reactor. Nuclear reactions, including fission and scattering, heat transfer in the coolant and fuel, thermal expansion of structural materials, and material degradation, including corrosion, occur mutually affecting each other. In order to determine the power and temperature in each tiny region, these governing equations for the neutron and temperature fields need to be solved. The neutron field is governed by the Boltzmann transport equation. The fuel temperature field is determined by solving the heat conduction equation. The coolant temperature field is governed by the mass, momentum, and energy conservation equations. The momentum conservation equation is the Navier-Stokes equation. All these equations are first principle equations. The first principle based cost calculation is, however, very difficult because of several reasons. The most important reason is the complicated dependence of cross-sections on energy, as demonstrated here for the resonance behavior. The macroscopic cross-section is affected by temperature through the strong temperature dependence of microscopic cross-sections and material density. In coolant, flow turbulence, boiling heat transfer, makes it almost impractical to solve the Navier-Stokes equation as is. Therefore, several approximations and simplifications were introduced in the conventional reactor calculation. Multi-group approximation of the cross-sections, homogenization of materials in the unit of assembly, and the diffusion approximation are those introduced in the neutronics side. In the thermal hydraulics side, various empirical correlations, such as Dietz-Boylte equation for heat transfer coefficient, drag coefficient, and turbulence mixing coefficients are introduced. Therefore, prior experiments were essential to generate these correlations. In addition, simplification of the coolant flow as 1D flow is introduced not only in the coolant pipes but also in the core as parallel 1D flow channels. The Parks code, which I wrote when I was a graduate student at Purdue University back in 1995, was a typical conventional reactor simulation code based on these approximations and simplifications. Even though the code was based on the two-group neutron diffusion equation, which is a very simple one, I had to work very hard to develop fast yet accurate solution method. This is the result of the Parks calculation for a control rod ejection benchmark problem. It shows that the reactor power approaches to a asymptotic level after this power pulse due to the strong Doppler effect associated with this rapid fuel temperature rise. This figure is the core power distribution, which shows very high peak at the ejected rod position. It is noted that the power distribution is shown in the unit of quarter assemblies, not pinwise. It is because each assembly is represented by homogenized cross-sections. In 2002, it was possible to obtain detailed sub-pin level core power distribution through direct whole core calculation, which does not involve any homogenization. At the time, I led the numerical nuclear reactor project, as the Korean side PI of an INERI program. The project was to challenge the first principle-based core calculation by solving the Boltzmann transport equation directly for the whole core, exploiting the parallel computing power of Linux clusters. The product was the Descartes direct whole core calculation code. Although direct whole core calculation was intended, the solution of the Boltzmann transport equation for the entire 3D domain was not possible because the computational burden was too high. Therefore, I introduced a novel idea of performing the transport calculation for each plane by using the two-dimensional MOC, namely method of characteristics transport solver. Each 2D transport solution, which is obtained with explicit sub-pin level geometry representation, is then used to generate pin homogenized cross-sections for each plane. Then the 3D problem is solved with the pin homogenized cross-sections in the coarse mesh finite difference, namely the CMFD framework. This method was named as planar MOC-based 3D CMFD calculation scheme. This was a breakthrough method that enabled direct whole core calculation on the Linux cluster at that time. Later, this method was adopted in the MPACT code, which was the direct whole core solver in the Vera platform. Bera was the primary product of the Castle project, which was a US government-funded big project for high-fidelity multi-physics reactor simulation. The term virtual reactor instead of numerical reactor was first used when they constituted Bera by combining the impact neutronics code, CTF thermohydraulics code, and the MAMBA water chemistry code. Bera demonstrated impressive performance in the simulation of so-called crud-induced power shift, or SIPS, which occurred in Watzba Unit 1 nuclear power plant. In cycle 7 of Watzba Unit 1, it was observed that the actual power distribution is bottom skewed. Namely, the power is more shifted to the bottom than the predicted ones in the cycle design calculation. Later, it turned out that it was because the crud formation at the top of the core, which is hotter than bottom. The crud absorbed boron in the coolant, so that boron is deposited at the top, causing the power shift to the bottom. Better simulation result clearly showed these multi-physics phenomena as shown here. Without the modeling of crud, the actual offset behavior shown here as the purple line is quite away from the measured values shown in the blue squares. With MAMBA, the actual power shape shown here with the green lines matches well with the measurement shown here with the red symbols. The spike here shown in the actual offset plot is due to the cleaning of the crud, which resulted in the removal of power shift. Vera predicted this spike very well, as shown with this green triangle. This Vera demonstration of the SIPS clearly showed the value of the virtual reactor for conventional reactors. Now let me move to the topic of virtual reactor for advanced reactors. These 7 SMRs are the typical water-cooled advanced reactors under development in various countries. These 4 are the integral reactors in which all the major components are placed in a reactor vessel. This integration makes the flow path complicated so that 1D flow simplification cannot be used. This flow modeling limitation becomes more severe in some reactors which employs passive core cooling. Some of the reactors do not use soluble boron, so that control rods and burnable poisons are extensively used to make the core very heterogeneous. In terms of both neutronics and thermohydraulics, these water-cooled SMRs pose challenges in the core calculation. The core calculation challenge is even bigger for the non-water-cooled reactors. These are sodium-cooled and lead-cooled fast reactors under development, and these are pebble bed type and block type gas-cooled reactors, and these are molten salt reactors with the molten fuel and or solid fuel. The advanced reactors in general have complicated geometry with severe heterogeneity. In gas-cooled reactors, which uses tiny trace of fuel elements, the heterogeneity is more severe, so that so-called double heterogeneity is present. The cores are small, resulting in high leakage. In the core with the severe heterogeneity and high leakage, the diffusion theory is not valid, so that transport solutions need to be obtained for the whole core. Also, slow flow speed associated with the passive cooling would require delicate fluid modeling. The corrosion issue in the molten salt environment must be properly mitigated. In this regard, sophisticated multi-physics modeling involving neutronics with continuous energy Monte Carlo, thermal hydraulics with CFD, and material degradation analysis with the atomistic scale material simulation are required to obtain sufficient solution fidelity. All these calculation models require enormous computing power. Fortunately, the GPUs which outperforms CPUs can be effectively used to mitigate the enormous computing power requirement for high fidelity analysis of advanced reactors. GPUs can yield high computing throughput by massively parallel SIMD and vector processing. Let me show you the power of GPU in SIMD, namely single instruction, multiple data mode.
Let me speed it up.
Can you hear the sound?
Yes, we can. Yes.
This is serial processing. And now,
Ladies and gentlemen, science class is now over.
this is the parallel processing with SIMD. The instruction to mix three basic RGB colors to produce a specific color in each pixel is the same. Only the mixing ratios are given differently with different data set for each pixel. In order to fully utilize the superior parallel computing power of GPUs, the computer code should be carefully written to exploit the SIMD operation. This is a new challenge in GPU programming. Another challenge is related with the small onboard memory of a GPU. Special care must be taken for efficient memory management. At Korea Atomic Energy Research Institute, we identified the elements of the virtual reactors for advanced reactor development as this. The first is neutronics with the GPU-based Monte Carlo code. The second is higher order DNS, namely direct numerical simulation for the solution of the Navier-Stokes equation. The third is CFD with the physics-informed AI. The fourth is atomistic material simulation using machine learning-based interatomic potential. Most of them involve extensive use of GPUs. Let me talk about each subject one by one. At my reactor physics research group at Seoul National University, we have been developing a GPU-based Monte Carlo code with the thermal feedback for superior computing performance in power reactor calculation. The name of the code is Pragma, which stands for Power Reactor Analysis Using GPU-based Monte Carlo Algorithm. It has a specialized geometry module for faster execution in regularly structured cores. For general geometry application, it uses finite elements and the optics ray tracing engine of NVIDIA. In order to maximize SIMD programming, many innovative methods, including event-based tracking, were developed. Also, efficient memory management was achieved by automatic domain decomposition. In most Monte Carlo codes, the history-based tracking scheme is used. This is to let each calculation thread track a neutron which would yield its own collision history that will be different from others. then each thread should execute different instructions because the collision of each neutron is random. This is not SIMD operation. On the contrary, in the event-based tracking, neutrons undergoing the same events, such as capture, scattering, and fission, are processed together by the same instruction. And by a sorting algorithm, it is possible to collect neutrons undergoing the same events. This is to fully utilize the SIMD operation. In the event-based scheme, one computing thread will track different neutrons at different times, like this. The automatic domain decomposition scheme, as shown here, is also essential in GPU computing because the memory on a GPU card is not enough to contain the entire geometry information of the whole core. These two examples show the elaborate programming is essential in GPU computing. Pragma's superior computing performance was verified first through the Beaver's real core benchmark problem. By using 24 commodity GPUs, the two-cycle depletion calculations with the full thermal feedback could be completed within a day. Of course, the results are very accurate and detailed. No Monte Carlo code can perform this fast calculation at this low cost. In general geometry representation in Pragma, all the objects are represented by finite elements of these four shapes. The optics ray tracing module in CUDA is used to trace neutrons instead of light. Optics provide a very efficient searching tool for finding the next intersection of a neutron track with an element by so-called bounding volume hierarchy algorithm. This is the result of the Pragma calculation performed with the optics ray tracing for the megapower heat pipe reactor, in which fuel rods and heat pipes are placed in a monolith structure like this, and 31 minutes with 24 GPUs were enough to obtain this power and temperature distributions. In order to handle special structure of the pebble type and the block type gas-cooled reactors, sphere and cylinder objects were specially added as tracer container. The core geometry is then described by an overlay of the finite element mesh structure and the two tracer containers. The location of each tiny tracer is explicitly determined by a rejection algorithm. The three layer materials within each tracer are explicitly represented as well. The delta tracking scheme is used to avoid overly frequent tracer region search. This shows the Pragma result for a block-type gas-cooled reactor. The calculation time is only 2 hours with 24 GPUs. This one is the Pragma result for a pebble bed type reactor. The location of each pebble was determined by the SOFIA smoothed particle hydrodynamics code, which can simulate the pebble packing like this. This is the resulting pebble distribution, and this is the power and flux distribution. In the graphite reflector, which is represented by a finite element, only the flux distribution is shown. Now let me move to the topic of direct numerical simulation for the solution of Navier-Stokes equation on GPUs. In most CFD codes, the lens, namely Reynolds average Navier-Stokes model is used. Lens involves averaging of the Reynolds stress term and empirical models are employed to properly represent the stress term in various conditions. DNS is required to avoid using the empirical terms, but DNS requires extremely small finite elements meshes so that it takes a huge computing time. If a higher order method is used to represent the internal variation within an element, larger elements can be used for the same extent of accuracy. However, with the higher order approach, the solution for each element would cause an increase in computing operation. The increase in element-wise computing operation is, however, well suited to GPUs. At Argonne National Lab, they ported the NEC 5000 CFD code onto GPUs by employing a higher order scheme called spectral element method. And they applied it to a molten salt reactor analysis. At CARI, we are investigating hybridized discontinuous Galerkin method for the more efficient GPU parallelization of DNS. It is named DYNA, which stands for Direct Numerical Simulation for Advanced Reactors using Hybridized Discontinuous Galerkin method. This shows the effectiveness of DYNA in a driven cavity problem. With the fourth order polynomial, only 18 coarse meshes were enough to reproduce the fine mesh solutions. Now let me move to the next topic involving machine learning. GPUs are known to be adequate to neural networks. For training a neural network, either model parallelism or data parallelism can be applied. The model parallelism is to use a GPU in a different layer of neural network. This is needed to construct a big neural network for deep learning. The data parallelism is to use the same neural network in different GPUs. It is to use each GPU to train with different input data sets. This is for big data applications. When solving a physical problem in which a particular physical governing equation can apply, it would be better to train a neural network with the physics constraint. It is called physics-informed machine learning. Once a neural network gives a trial output set consisting of spatial distributions of physical quantities, the output set is given to a residual evaluator network which can evaluate derivatives from the distribution and calculate the residual, which is the difference between the left and right-hand side of the governing equation at each spatial point. The residual information is fed back to the neural network so that the neural network parameters are adjusted to minimize the residual. This is one way of physics-informed machine learning. The basic training data are generated from high-fidelity computed solutions at limited conditions. CFD is a good area of physics-informed machine learning. This is an example which involves 10 CFD solutions for a 2D flow around the cylinder. 4 CFD solutions were generated with the different aspect ratio of the cylinder, 3 with different angle of attack, and 3 different viscosities. These 2 are the governing equations of the flow which will be used for the residual evaluation through differentiation. These videos compare the goodness of the physics-informed machine learning for continuous bearing, angle of attack, aspect ratio, and viscosity. The results shown above were obtained by training with only 10 sets of data, no physics. And the bottom ones were trained with the physics as well. It is obvious that the bottom ones are much closer to the reality. Atomistic material simulation, represented typically by molecular dynamics, are used to predict material characteristics such as impurity behavior and solubility. For molecular dynamics calculation, interatomic potential, shown as this, is used in the solution of the Newton equation of motion for a group of atoms given in a lattice structure like this. The interatomic potential can be obtained by quantum mechanics calculation, which takes a lot of computing time. Machine learning can be used to generate interatomic potential generated from some selected structures, as illustrated here with big circles. The red line here are those generated after machine learning on a neural network. This entire loop here is an active learning process in which the new structure beyond the prior range are suggested by the transient molecular dynamic calculation. For the new structures, the quantum mechanics calculations are additionally performed. This active learning process makes the machine learning more accurate and powerful. This movie demonstrates the molecular dynamic simulation of liquid sodium with the gas oxygen. The interatomic potential for this calculation was obtained by the active machine learning. Once this kind of molecular dynamics calculation can be readily performed, a large number of combinations of liquid metal elements like this can be examined to find an alloy that has benign characteristics. So it can be used in new material development. Finally, let me show you a digital twin of the Korean APR 1400 power plant. It is a replica of a real plant and was generated from the CAD drawings. By integrating monitoring data and simulation engines, the local state of the plant can be realistically followed. We are now going into the turbine building. And let's look at this pressure and the temperature at the inlet of the turbine and also outlet of the turbine. The maintenance record can also be accumulated for each part. This kind of digital twin will help the safe and high performance operation of the plant. This is a water drone, which is used for the inspection of the filters in the internal refueling water storage tank. Now let me conclude. By exploiting the increased computing power, it is now possible to build a virtual reactor with the first principle based modeling and simulation of each physical phenomena. Examples are Monte Carlo neutronics, DNS of Navier-Stokes equation, and atomistic material simulation. The virtual reactor will be useful for accelerating advanced reactor development by saving time and resources needed for experiment. The enormous computing power requirement can be resolved by using GPUs and elaborated programming. Proper SIMD parallelization and efficient memory management are necessary to fully utilize the capability of GPUs. Machine learning can also be a promising way. Yet, a lot of further development are to be done to realize virtual reactors. And it is up to you, young folks. Thank you for your attention. While you are thinking of your questions, let me show you another digital twin. It will take 2 minutes. Now we are going into the containment. So this is the reactor core, and we see the 2 steam generators. And we'll go below. This is pressurizer, I think. This pressurizer. We will go to the bottom, which is the internal refueling water storage tank. We will see the bottom soon. Okay, this is the water tank. We are inside. We are going up again. I think this is a very fancy digital twin, very accurate and detailed. Now we are out. Okay, I'm done with my presentation. If you have any question, I'm happy to answer the questions.
Okay, thank you very much, Professor Zhu. It has been a very interesting webinar with a lot of attendance, I can tell you.